how do we simulate the exchange of resources in SimPy, where we're queuing for one resource where we're already holding another? By the end of the video, not only will you have the skills to implement resource exchange within your own SimPy models, you'll also have the knowledge of how to set your model up so that it's nice and simple to check that the logic is working as expected. I'll illustrate this using a stroke pathway model. We're going to have stroke patients arrive to that model following an exponential distribution, and on average every 1.5 days there'll be a patient arrival. They'll need to queue up for acute treatment in a large hospital, and to be admitted to the ward they'll need a space, an acute bed. Once that treatment's completed, on average every 7 days, they'll be medically fit to be transferred to a rehabilitation unit in another hospital. So they're sort of queuing, but they'll still be in their acute bed. In order to be transferred, there needs to be a space within the rehabilitation unit. And so in SimPy terms, we're going to try and seize a rehabilitation bed. And we won't release our acute bed until that rehabilitation bed becomes available. So we have this resource exchange idea, and admission to the stroke unit will be blocked until that resource exchange takes place. I'll take you through some of the setup of the model first. So I've got some constants here that I'm using for my default values within the simulation model. So for example, we've got the mean inter-arrival time of stroke patients. We've got some counts for the resource numbers of beds that are available. And then we've got the parameters of our log normal distributions that we're going to use to represent the acute and rehab length of stay. I've got a helper function here called trace. That's just going to wrap the print function, and it's going to allow me to show some debug information or hide that depending on what I want to do. I've created an experiment class, and that's going to encapsulate all of the parameters, probability distribution, and results for a run of the simulation model. Now, I won't go through the design of this in detail in this video, but I will link at the top now to a very detailed video which describes how to set up your simulation models so they're nice and easy to use in experimentation. A few highlights to include are that this is where the resources for the SimPy model are going to be contained. For the acute ward, that's going to be named acute ward. For the rehabilitation unit, that's going to be named rehab unit. So when we request resources, we're going to be using these two variables. We have some sampling distributions in there as well. So we have the arrival process, we have the acute length of stay distribution, and we have the rehabilitation distribution. But all of the things we need to do to implement resource exchange are actually contained within the pathway logic itself. I've defined a process called patient pathway. That's going to accept 3 mandatory parameters. A patient ID, that's just an integer value, a unique value so that we can check which patient is which. env, that's a SimPy environment object. That's the engine of our model, allowing us to check the current time. And args, which is of type experiment. And remember, that contains the parameters and sampling distributions that we use within our model logic. So to begin with, the logic is very simple. We're going to track the current time, then we're going to request a bed from the acute ward and wait for that bed to become available. Once we've got that bed, we'll track the current time and we'll store the waiting time in our results within our experiment. There's a trace request here, and that will display if we want to have a look at what's going on. Then we simulate the treatment on the acute ward by sampling from the acute length of stay distribution and yielding a SimPy timeout. Now, after that point, the patient is medically ready for rehabilitation and could be transferred if a bed is available. So we're going to track what time that medically fit for transfer commences, and we'll print that out to the user. And then we're going to request the rehabilitation bed, but we're not going to use a with context manager here. Instead, we're going to directly call request from the rehabilitation unit and store that request in a variable called rehab bed, and we'll yield that. So there's no context manager here. We're still within the indentation for the acute bed resource. That's key. If, for example, this was not indented within that with context manager, SimPy would automatically release the resource, which isn't the behavior that you want. So here what we're doing is queuing up for the rehabilitation unit while we're still holding on to the bed within acute. Once that's available to us, SimPy will move to the next line of code. And here we're tracking the transfer time, and we've worked out how long the bed blocking time was, and we're saving that to results as well within a list called bed blocking times. And we'll print that out to the user, as well as some debug information about how long the waiting time was, and that we'll use that to track to see, is our simulation logic working as expected. So now that we have that rehabilitation unit, we can release the acute bed. So now the indentation is one less. So if we scroll back up, we can see that we're no longer within the with context manager for the acute ward. So SimPy has automatically released the acute bed. Now what we're doing is simulating the patient's stay on the rehabilitation unit. So we sample from the rehab length of stay distribution and pass that to an environment timeout. After that's completed, we track the discharge time, and we have to manually release the rehab resource. That's something we've not done before because we've always used with context managers. That has an automatic teardown or automatic release of the resource built into it. Here we need to explicitly call rehab unit.release and pass in that rehabilitation bed request. If you're finding the content of today's video useful, please smash that like button, it helps out a ton, and also subscribe for more content. The model also has a standard arrivals generator for strokes. That's going to accept the SimPy environment and experiment arguments. We've got a standard loop here where we are sampling the inter-arrival time of the next stroke, delaying the simulation for that length of time, and then scheduling the next event, which is the patient pathway process to kick off immediately. To run the model, as always, we have a single run function. So we pass in the experiment, the replication number, which we'll use as the seed of the simulation model, and how long we would like to run the simulation model for. In this case, we're defaulting to 100 days. So within single run, we initialize the result variables, we set the random seed for the run, we create our SimPy environment. Now that we've got an environment, we can set the experiment's resources. So we would create the acute ward and the rehabilitation unit. So SimPy.resource, that accepts the SimPy environment and also the number or the capacity of resources that you require. And then we kick off the stroke arrivals generator and we run for 100 days. And then there's a little bit of code at the end, and all that's doing is calculating the mean acute waiting time and the mean bed blocking time. And we're going to return that results, which is a dictionary, to the caller. So to run the simulation model, all we need to do is create an instance of experiment. Then we call the single run function, pass in that experiment, and we return the results, which will print to the screen. We'll also turn trace on. So we'll see the log of the simulation model as it runs for those 100 days. So we can see initially that patients are admitted immediately to the acute ward, and also patients are admitted immediately to the rehabilitation ward. That's because the model is starting from empty. In this example, we're not going to worry about warm-up periods or initial conditions. Instead, we'll just scroll down and take a look for when bed blocking starts to take effect to make sure that our model is working as expected. So we can see here that patient 17 was medically ready for rehab on day 40, but they weren't transferred to rehab until day 41. So they actually blocked an acute bed for just over a day. Patient 19, on the other hand, was ready to be transferred on day 41, but they were actually transferred on day 45. So they delayed for over 4.5 days. So that confirms that our resource exchange appears to be working as we expected. We can also see some waiting times in the model. So we can see that it takes just over a day to be admitted to the acute stroke unit, and it takes around 4.3 days to be admitted to rehabilitation once the acute length of stay is complete. We'll finish off by just doing a few checks of our model logic. I'm going to turn trace off for this. I'm just interested in the quantitative results at the end. And what I'm going to do first is I'm going to remove all bed blocking from the model. In SimPy, I'll do that by setting the number of rehabilitation beds to 1 million. And we can see here that we've got no bed blocking. And what that's led to is everybody being able to admitted to the acute stroke unit immediately. So all of the delay that we saw in admission in this setup of the model was due to bed blocking in rehabilitation. All of the code that I've demonstrated today is available on GitHub. I'll link to that in the description below. This tutorial comes with an interactive notebook you can run directly on your computer without any installation using Jupyter Lite. There's a link here within the GitHub repo. If you click on that, Jupyter Lab will automatically launch for you. And we were in Notebook 11 blocking. If you double click on that, this will run natively within your browser and you have all of the code available to you. If you need a more basic introduction to using resources within SimPy, you need to watch this video that's on screen now, and I'll see you next time.